Hi, I'm Carden Baylor, and I want to talk to you about using pathfinding to model disruptions in the New York City subway using graph analytics with pandas data frames. The MTA subway is the largest in the country. There's 3.6 million Americans who ride it each day, which is 1.3 million more people that ride the subway than take a flight each day in the United States. The New York City subway is only one of a few in the world that run 24/7. So in that case, the New York City subway is unique in the number of riders, stations, and level of service it provides, and a closed station ripples throughout the entire system. Using Aura Graph Analytics, we can easily model what would happen if a station was fully closed for repairs. And insights like this apply not just to transportation systems, but to supply chains and manufacturing processes and much, much more. So how can we model disruptions in the MTA? Like I said, the New York City subway is unique in its number of riders, stations, and level of service, and a closed station will ripple throughout the entire system. But using Aura Graph Analytics, we can easily model what would happen if a station was fully closed for repairs. Insights like this can apply not just to transportation systems, but to supply chains, manufacturing processes, and much, much more. So just to quickly talk a little bit about the architecture of Neo4j Graph Analytics. The way it works is we spin up a serverless session that allows you to run graph analytics against Python data frames. In this case, we're going to be starting with CSVs. So how it works is you get a CSV, you put it into a Python data frame, you spin up a session, you run the algorithms, it puts it back into the data frame, and you could potentially put it back into a CSV or back to a SQL database or wherever you get it from. We have a JPEG here. You probably wouldn't put a JPEG into a Python data frame, but you could perhaps put metadata about it into a data frame and use that to run graph analytics on it. So the algorithm we're going to be using today is called Dijkstra's algorithm. I want to set the stage a little bit. Imagine you're starting with a set of nodes, in our case subway stops, and you have a couple lines connecting them. And we want to find the shortest path between 2 points, A and F. Our algorithm will calculate the distance between A and all other nodes between A and F. So let's take a look. We're trying to get from A to F, and let's pretend that these are caves. From A, there's some chambers in the cave system. We're trying to find the quickest way to get from A to F, and for whatever reason, instead of just walking out, you want to calculate what the shortest way is out and then do it. You can have different weights on these edges, and that will determine what the shortest path is. So how it works is it's a greedy algorithm. So we're going to start with A, and we're going to calculate what's the shortest distance from A to A, starting with the nodes that neighbor it. So starting with A, the shortest distance to A is 0. We then look at the two adjacent nodes, B and C. C is 2 away from A, and B is 6 away from A. So the quickest path so far is to go through C. From C, you could either go to B or to D. If we were to go to D, the quickest path back to A would be 10 through C to A. So 8 plus 2 equals 10. Through B, it would be 5. So A to C to B, so B, 3 plus 2 equals 5. So now we're looking at B. We already know the only unvisited node that's a neighbor of B is E, so we're going to go to E, and that would be 9, because 5 plus 4 equals 9. From E, we could either go to F or to to D. If we were to go through F, it would be 9 plus 3, which is 12. Or if we were to go to D, it would take longer to go to D than it would be to go through the original path to D, so we don't update that number. Finally, we're at D. The quickest path, if we're going this way to F, would be 3 plus 8 plus 2, and that would be 13, which is more than the original path through through C. So if you go through C, or rather, if you go through C, it would be, or if you go directly to D through this kind of elongated path, it would be longer than going direct. So we're just not going to update it. So now we have all of the paths from every node to A. The one we're interested in is F, and you can kind of walk backwards. You go F to E, E to B, B to C, C to A, and that's your path. So we're going to take a look at this in a notebook. Now we're going to take a look at a notebook that runs through how to use Dijkstra's algorithm on the New York City subway. So first we're going to install the latest version of the package, and we're going to include our client ID and secret and tenant ID in order to access Aura Graph Analytics. We're going to load in our packages, then we're going to create a session. Then we're going to estimate, or we're going to create a session object, and then we're going to estimate the size of the session we'll need. I made a pretty low estimate. You're actually going to need a bigger one, but it gives you a little idea that this can run even if you get your estimate wrong. So then we create our session. We're going to call it GDS. We're going to load in two CSVs as pandas data frames. If you wanted to use the results from a database or something like that, you could do that. As long as you can get into a pandas data frame, you can use Aura Graph Analytics with it. Next, we're going to create a projection. So our projection will need to have a couple things. For the data frame representing relationships, you'll need to have a source node ID, a target node ID, and a relationship type. For the one representing nodes, it's just going to need a node ID. So we're going to clean up our data a little bit. It also has to be directed graphs, so you can't have an undirected relationship, meaning that this can't, if this goes to here, it won't also assume that that goes back to the source node. So basically I'm going to just do a little cleaning to double the size of this so that it gets both directions in it. And then here's the node IDs, like I said. And finally, to actually project the graph, which puts it in memory and allows you to run algorithms against it, we're going to use graph construct. So we're going to name our graph subways, and then if it already exists, we're just going to drop it. Then we're going to use graph construct using our nodes and lines data frames. Do that. Finally, we're going to use Dijkstra's shortest path to see how we can move through the system efficiently. We're going to create a simple wrapper function below, so we'll be using the names of the stations rather than just their IDs. So don't worry about that, but here's the important part here. GDS, shortest path, Dijkstra, and then you stream the results. That way you get them back in your notebook. So the source station is going to be Grand Army Plaza in Brooklyn, and the target station is going to be Times Square in Manhattan. So we run this and we say, get the shortest path between the two. Currently, I'm not using anything like weights in this relationships. So it's just going to do the least number of hops. You know, a more fleshed out example might include, you know, the tracks, trying to minimize switching lines at stations or something like that. But this is literally just going to look at the least number of hops between the nodes. So it says Grand Army Plaza to Bergen to Atlantic to Canal to Union Square, Herald Square to Times Square. But what if one of those stations closed? What would then be the shortest path there? So we're going to create another function to exclude some nodes and see what would happen if Herald Square was closed. So we do that. Its ID is 230 right there. We create a new projection that doesn't have those nodes and relationships in the graph that it's modeling in that projection. And then we run the same thing again. We get a different path this time, Grand Army to Bergen to Atlantic to Canal, and then here's where it changes, to Chambers to Penn Station to Times Square. And yeah, you can use this to model all sorts of things. Like you could be using this for suppliers in a supply chain. If some suppliers went out of business or if they became heavily tariffed or something like that, you could then model a cheaper using the weights between the different suppliers, like costs. You could model that, or really anything else that where you're trying to optimize some sort of path between nodes. Doesn't have to be time, could be cost, could be really anything. And then once you close your session here, the billing will stop for your algorithms and you will be all set. Now you've seen how you can model disruptions on the New York City subway using Aura Graph Analytics, starting with just pandas data frames, and you can achieve powerful results without having to do an ETL into a full graph database.